Alright, so we're going to take what we have so far and we're going to use it to find our solution now. And so we're kind of going backwards as we're going to say, well, if the thing I have made has these parts, so I'll come all the way up here, these two parts are some generating function, well, I should be able to integrate my way back to that function. And so let's integrate our way back to the function. Let's come here. And what we're going to say is, if we remember, that was our m part. And I'm keeping the function of xy out. Remember, these are multivariate in their nature, but we're focusing on them one variable at a time. We're using the fact that our single variable function exists in a two variable plane, right? The independent variable and the dependent variable make a plane, and we're exploiting that fact by jumping up a dimension. Which you kind of have to do a lot. A lot of times things project down into the space you're working in, and you have to sometimes jump up a dimension in many different ways. I mean, I know right now I think a dimension is a physical concept, but think of time as a dimension, and any measurable parameter as a separate dimension, and sometimes adding a dimension gives you a place for your solutions to move through, just like complex numbers, which you'll be greeted with very shortly. But anyway, my goal here is I want to integrate this. So I can say that f of xy is going to be the integral of m as a function of xy dx plus, instead of the constant, I'm going to grab all of my y variables and have g as only a function of y. Now, because I've been forcing these derivatives to focus on one side of the variables, I'm going to say, hey, m's taking care of all the x stuff. Remember up above in the equation, it was mxy dx. And I'm going to say the other part of y is just going to be contained in this function. And so where our constant of integration would have fallen out, it falls into what the values of y could be. And so this tells me how to get part of my function. And it proves that this works. But there's a step we have to do to stitch it all together. Now, in the proof version, this looks ugly. Right? That always looks ugly to me. Doing my notes last night for coming into class, I read over this 10-15 times to make sure I was explaining it properly. I want to find this part. I have thrown everything into some function of y. Well, to express my solution, I need it. Well, over here, I have something that's dealing with y. So I come out here and I take a partial of what I just found in respect to y. And so what I end up doing is by taking the partial, this whole thing is going to end up equaling n. And so I take the partial of y to whatever the answer is that comes out of this integral. Now, it looks like I haven't done the integral, but when we go to solve, we will do the integral. This will be a function, and we can take the partial with y. And that's the part that looks ugly. And if I take the derivative of some function only in y by y, I get g prime. And this will help me, because now I can say g prime is equal to this thing minus the derivative with respect to y of whatever answer I got out of this. and this thing is n. And so we integrate g prime to get g. And that'll be g to some arbitrary constant. And once I have g of y, I can come back up here and I can stitch it into here. And I will have my full f of x plus some arbitrary constant. But as I scroll all the way up, f of x was equal to an arbitrary constant. So I can take this whole thing and throw the constant into it, and I get my function. This series of steps here looks ugly. So I'm going to continue with our example in the next video and lining it out. What we do stepwise, and what I'm going to do in the example is 1. Test for exactness, which I've already done. And so the partial of m with respect to y should equal the partial of n with respect to x. And that's going to say, hey, these are exact. They're set up in a way that I can proceed. Once they're exact, I set my function that I'm looking for equal to m of xy dx plus g of y. Now, I'm going to do this in terms of x as the first function. It is completely logical to also do it this way, where you focus on y and you have your unknown function be dependent only on x. It's the same, you're just focusing on other parts. And sometimes n is easier to integrate than m in this form. So these are reversible between the independent and dependent that you do. For now, I'm going to focus on talking about this way. Just realize that if you integrate n, this is with respect to y, and this has to be with respect to x. Right? You're switching what you're using as your independent and dependent variables. Step 3, whatever comes out of that, right? We take d, we take the partial with the other variable. So again, I'm focusing on this version of it. Of f of xy. Let me just put this in words instead of math symbols to both sides. Both sides of the results of step 2. I keep hitting that button. Ooh, small, big. There we go. There we go. To step 2. All right, so we take the partial to step 2, and then we substitute n in because n equals df dy. Solve for g prime. Integrate g prime and sub into the results from step 1. And this is our solution. Implicitly, to C. Alright, let's do that with the example we have been doing. Alright, so I'm going to continue, and I'm going to number out our steps. So let's see here. Do I have enough room? No, I don't. What I'm going to do is I'm going to save this off, and we'll come back and I'll finish the videos with the rest of the example.